Hey everyone, welcome back to the Deep Dive. Today we're tackling one of the biggest questions out there, really, about the universe. We have a pretty good handle on the beginning, the Big Bang. Happened about 13.8 billion years ago. Just this incredible explosion, setting everything in motion, leading to this ever-expanding cosmos we see. But if it had that kind of start, what about the finish? How does it all end? It's funny, the Big Bang feels almost like accepted fact now, scientifically speaking. But the end, that seems like a much deeper mystery, something scientists have been wrestling with for ages. So that's our mission for this deep dive. We're going to explore the three sort of main ideas that cosmologists have put forward for the universe's final chapter. The Big Freeze, the Big Crunch, and the Big Rip. And these aren't just science fiction, right? These are possibilities rooted in actual physics.
That's exactly right. They're theories built on observation and our understanding of physical laws.
Yeah.
And what's fascinating is how incredibly different each outcome is. Each one suggests a totally distinct destiny for everything. So yeah, I'd invite you to really think about these potential cosmic finales.
Okay, let's jump in. Maybe start with the Big Freeze. It's also called heat death, I think.
Mm-hmm. Heat death or the Big Freeze.
And this one seems to have the most backing right now, based on what we're actually seeing.
It does, largely because we observe the universe's expansion is accelerating. That's key. The idea here is driven by dark energy, this mysterious repulsive force that just keeps pushing everything apart forever. Galaxies drift further and further away from each other.
Right, so things get really spread out.
Incredibly spread out.
Yeah.
So much so that eventually the gas clouds needed to form new stars become too thin, too diffuse. Star formation basically stops. And the stars that already exist, they just, burn out.
They use up all their fuel.
Exactly. They cool down, fade away, leaving behind remnants like white dwarfs, neutron stars, and eventually black holes.
Wow, that paints a pretty bleak picture, doesn't it? Just cold emptiness. Our research mentioned something about maximum entropy, like everything just gets completely uniform.
Precisely. Entropy always increases, meaning disorder increases. In this scenario, the universe reaches a state where energy is so evenly distributed that no useful work can be done. Nothing interesting can happen. No temperature differences, no gradients.
But no life, no processes, just stillness.
Almost perfect stillness. And even those black holes, which seem so permanent, theory suggests they'll eventually evaporate too through Hawking radiation. It's a quantum effect.
Hawking radiation.
Right.
So even they disappear over unimaginable timescales.
Vanish into just a whisper of particles, leaving behind, basically nothing. Just a vast, dark, incredibly cold void approaching absolute zero.
And time itself sort of loses meaning.
In a way, yes. If nothing ever changes, if there are no processes unfolding, does time even matter? It's a philosophical point, maybe, but rooted in the physics. It's not a dramatic bang, but a long, slow, quiet fade into perpetual darkness, a cosmic yawn into oblivion. Okay. But what if it's not so quiet? What if things go the other way? That brings us to the Big Crunch, right? The sort of opposite idea. Exactly. The Big Crunch scenario imagines that the universe's expansion doesn't go on forever. It suggests that maybe, just maybe, gravity could eventually win out over dark energy and expansion.
So enough mass, enough stuff pulling everything back together.
If the overall density of the universe is high enough, yes, gravity could halt the expansion and then pull everything back inwards.
So instead of galaxies drifting apart, they'd start rushing towards each other.
Yes. The whole universe would begin to contract. Galaxies would collide, merge, stars would crash into each other, and as everything compresses, the temperature would skyrocket.
That sounds intense. A complete reversal. So if that started happening, we'd see galaxies blue shifting instead of red shifting eventually as they come towards us.
That would be one sign, yes.
Yeah.
Over billions of years, this contraction would accelerate. Everything, all matter, all energy would collapse back towards a single point.
A point of like infinite density and temperature. Like the Big Bang, but in reverse.
Very much like the initial state of the Big Bang.
Right.
Which, leads to some interesting speculation.
Could it trigger another Big Bang? A cycle.
That's the idea behind the cyclical universe, or Big Bounce models. A universe that expands, collapses, and then bounces back in a new Big Bang, potentially forever.
An eternal cosmic heartbeat.
It's an elegant idea. However, it's important to stress that our current observations, particularly that accelerating expansion we mentioned, they don't really support the Big Crunch right now. It seems less likely today.
So interesting theory, but maybe not where the evidence points currently?
Correct. It remains a key concept in theoretical cosmology, but the data leans towards continued expansion.
Okay, so we've had the slow fade of the freeze, the fiery collapse of the crunch. What's the third one? The Big Rip. That sounds violent.
It is conceptually the most violent end. And like the Big Freeze, it hinges on dark energy
But in a different way.
in a much more aggressive way. The Big Rip scenario hypothesizes that dark energy might not be constant. What if its repulsive force actually gets stronger over time, like exponentially stronger?
Okay. So it pushes things apart even harder.
Much harder. So hard that it eventually overcomes not just the gravity between galaxies, but the gravity holding galaxies together.
Whoa! So it would literally tear galaxies apart?
First galaxy clusters, then the galaxies themselves. Stars ripped away from their orbits.
And it wouldn't stop there, based on what we read. Solar systems, planets.
It keeps going. The repulsive force becomes so dominant it overcomes the electromagnetic forces holding molecules together. Then the nuclear forces holding atoms together.
You mean it would shred matter itself, down to the atom?
Down to the atoms, then the nuclei, then even the subatomic particles. Everything gets pulled apart.
That's hard to even picture.
And in the very final moments, according to the theory, the fabric of space-time itself is torn asunder. It's not just cooling down or collapsing. It's a complete and utter disintegration of reality at its most fundamental level. Total annihilation.
Goodness, that's definitely the most dramatic ending. So, all right, we've got the big freeze, cold, dark, quiet emptiness, the big crunch, fiery collapse, maybe leading to a new beginning, and the big rip, just total violent destruction of everything, even space and time. Three incredibly different possibilities for how it all might end.
They really are stark contrasts.
Yeah.
And while, they're built on solid physics and decades of observation, the honest truth is we don't know for sure. Nobody does. Which one, if any of these, is correct? Well, that's still an open question. The universe's story is still being written, and we're constantly gathering new clues about its ultimate fate.
It's just mind-boggling, isn't it? Thinking about these timescales and these forces. So I guess the question for everyone listening is, what does all this mean for us? Stuck here on our little rock.
Well, on human timescales, none of these are immediate concerns, thankfully. But I think contemplating these cosmic ends, whether it's the cold silence, the fiery rebirth, or this chaotic ripping, it really underscores how mysterious and truly awesome the universe is. Its end, whatever it may be, will likely be as profound and awe-inspiring as its beginning. And for now, you get to be here looking out, wondering about it all, an observer in a cosmos whose final chapter is still unread.